Let's get started. Today's topic is IP 101. Today's presentation was created by Paul Rodriguez of Comcast. Due to a family emergency, Paul will not be with us today, so our speaker will be Steve Harris, SCTE's Director of Advanced Network Technologies. Now, I would like to turn today's SCTE live learning session over to our speaker. Steve, you have the floor.
Thank you, Susan. Welcome, everyone, to SCTE Live Learning and our IP Basics or IP 101 broadcast. So today's agenda is IP terminology. So we'll start off with some of the different terminology, bits and bytes and octets and stuff like that, just to get you familiar with those. We'll talk about the classes of IP. So we'll talk about A and B and C and those different classes. We even get into a little bit of D and E as well. We'll even talk about subnetting. So we'll say, okay, what is the advantages of subnetting? Why do we do it? Variable length subnet mask. You know, how does that differ from subnetting? Where does it used? And a little bit of an intro to IPv6, because if you haven't been following the news, we can see that IP version 4 has been running a little bit low, and IPv6 is coming out, and a lot of the MSOs and cable operators are looking to implement IPv6, or have done so already. So IP basics. So some of the terminologies that everyone in the IP field should be familiar with is a bit. Okay, so a bit is a binary digit, which is basically a 0 or 1. In digital, 0 is off and 1 is on. But this is the basic fundamental block for an IP address. So a lot of the times when you're learning IP, it's important to be able to break it down to binary so you can get into the subnetting and understanding the classes and how they're built. Another piece of terminology is the byte. This is basically when we take 8 bits and bring them together, we call this a byte. In other words, also referred to as the octet. Octet meaning octal, or 8 bits together. Now what a typical IP address looks like is what we call dotted quad, where there's 4 sections, and each section has an octet in it, worth 8 bits. So if you have 4 sections, 8 bits apiece, gives you a 32-bit address. Your network address. So part of the portion of an IP address, whether it's IP version 4 or IP version 6, you're going to have a network identifier or a prefix. And at the same time, you'll have a host portion or an interface portion that refers basically if it's a printer or router or switch that has some IP connectivity for management. Another piece of IP terminology is this broadcast address. So a broadcast address allows us to communicate on the IPv4 network within a broadcast domain. So that means that these broadcasts will not pass a router, but will pass through switches. And broadcasts, just so you know, have been removed in IPv6. And then the directed broadcast. The directed broadcast is directed at a particular network. In this case, this example is showing 192.168.1.0. That is the network ID. So we're actually broadcasting with all ones. 255 in decimal is equal to 8 ones in binary. Using all ones, we're broadcasting to the 192.168.1 network only. So what is binary? So I don't know if you've seen this chart. This is one of those charts that are thrown out there at you as soon as you get into any IP course. They throw a chart up on the board and say, okay, let's start converting decimal to binary. And I'm sure you may have seen this or run across it on the internet. Well, the idea here is to show everyone how to take decimal, which the IP addresses are written in, and convert them into binary so we can manipulate them, whether it's subnetting or variable length subnetting, or just understanding the different subnet masks, especially when a subnet mask is like a 255.192. The 192 is is significant and has some meaning on the subnet, so I need to understand what it looks like in binary. So this chart that I have here, I'm just going to highlight a couple things here. Let me just bring out my pointer. And if I come up over here, we have across the top is the powers of 2. Now why 2? Binary is base 2, where hex is base 16 and decimal is base 10. So it's going to be 2 to all the powers. Anything to the 0 power is always going to yield a 1. So you can see it's a 1 right there. And then 2 to the 1 is itself. So anything to the first power, or 16 to the first power, or 10 to the first power will always be itself. And then we have 2 to the second, which gives us 4, so forth and so on, 2 to the third. And a lot of times when you see this chart, you don't see this upper portion of all the powers of 2. You only see the 1, 2, 4, 8, 16. So one of the things you can do to kind of understand this chart is, well, I don't really care about 2 to the powers and across the top. I can just, it's very easy for me to remember 1 and double that is 2, double that is 4, double that is 8. And that is fine, especially when you start going past 8 bits, what we have here. And we chose 8 bits because of the octet. So when we go into 9 bits, we just take 128, we double that, we get 256. And then down here I have some samples. Well, actually, Paul has some samples here of the different numbers that are broken down. So really what you have to ask yourself as you go through a number, and this one's pretty simple, is how many 128s are in 1? Well, obviously there's 0, and we can continue that all the way across. We get over to 1, obviously there's 1, 1 in 1. But if we jump down to 32, we say, okay, let me go down the chart. Is there any 128s? No, there's no 64s. There is a 32, and pretty much that's it, and everything else gets zeroed out. So as you go through these different values, say if you had one on here that was a 10. Now I have 8, but I don't have a 10. Well, a 10 would be an 8, would be a 1 there, and then over here where there's a 2, in this column there'll be a 1 there. So that's what a 10 would look like. So it's just basically saying I can use 1 or 0 of the values across the top to make up decimal numbers. And this chart will go to 2 to the 8th power, which is 256 possibilities. Why 8? Again, going back to the octet. And 2 to the 8th gives you 256 possibilities from the range 0 to 255. So you can't have anything less than an octet than 0, and you can't have anything greater than an octet than 255. So here's some additional numbers. Let me just move my arrow out of the way. Some additional numbers. There's that 10 I was talking about. Here's a 172 broken down. And a 255. Notice 255 is all 1. So the important takeaway on this slide is the 0. Because if I put all zeros in the host portion of an IP address, that is the network ID. And when I put all 0, or all 1s rather, in the host portion of an IP address, all 1s is the broadcast ID. So it's very simple. You can see all 1s. And when I add this all up, it's going to add up to 255. But I'll give you a little trick here. If you take 128, and if everything's turned on to the right of it, everything has a 1 in it, all the way across, then that's always 1 less than 128. The same thing here, so that means 127 and 128 is 255. If I go over here to 64, everything to the right of 64 must be 63. So it's very easy for me to say, oh, okay, well, 64 plus 63, it just makes it a little bit faster math for me, so I don't have to add up everything individually. So it's a little trick on the chart. So let's take a look at some address examples. I'll just throw my arrow over here to the right. So we have the network address that I spoke of, and here I'm showing a Class C address. Now the Class C address doesn't have as many hosts, and we're going to see that coming up. So if we go into here, it says I got a 192.168.1.0. So we got 4 octets. We know that they're all decimal, and that there's some type of binary representation here. In a Class C, the first 3 octets are network, and I said that's coming up, and I'm going to show it to you. And the last octet is host here, and here we have all zeros in the host portion, so that's how we identify to the network device that it is a network ID. Our broadcast address, putting all 1s in the host portion, as we showed earlier in the previous slide, that all 1s or 255, and here's 255, in the host portion, which means all 1s. Then we have host IPs. So if you look at the host IPs, for this particular one, a Class C, again, only has a single octet for host. So single octet being 8, 2 to the 8th is 256. Well, that's 0 through 255. Well, 0 I can't use, and 255 I can't use, because they're special addresses. So that's why our host portion will start with 1 and go to 254. And we have to actually kind of subtract 2. So really, 2 to the 8th is 256 minus the 2, the network ID and the broadcast ID, gives us 254 usable IP addresses. So the classes, what do they look like? Well, here we have the A class. So in the A class, here's the network portion, and then there's 3 portions for the host. So in the network portion, the way we figure this out is that there's 8 bits. Well, one of the bits I can't use. That's the first bit. because if I start changing the bits around on all 8 bits, I fall out of the class. So really I only have 7 bits I can manipulate here. So 2 to the 7th will give me 126. Or sorry, 2 to the 7th will give me 128. And I can't use 127 because that's a local loopback. And I can't use 0 because that's a default gateway or gateway of last resort. So what we're saying here is that Class A networks go from 0 to 127. We can't use 0 and we can't use 127. And then the rest of the octets all belong to the host. So that is 8 bits here, 8 bits here, 8 bits here. That's 24 bits, or 2 to the 24th power, or 16,777,216 IP addresses on a Class A network, minus 2, because you can't have the network ID and you can't have the broadcast ID. Let's take a look at the Class B. Class B, the first 2 octets are network. And out of those, there's 8 bits here and there's 8 bits here, but we can only use 14 of those bits, because if I manipulate all 16 bits, I will no longer be a Class B. So I kind of call them lock bits. Everybody kind of refers them as different things, but we just cannot manipulate those bits. If we do, we will not stay in the range of 128 to 191. So 2 to the 14th is the number of possible networks here, or 16,384 possible B networks. And over here is the host portion. And the host portion here, we have 8 bits here and 8 bits here, which is 2 to the 16th, or 65,536 hosts per Class B, minus 2, of course. The Class C, which was the previous example, said we would get to it. Let me just kind of move my arrow out of the way. Is 3 octets of network, and we can only use 21 of those bits, because if we change the other 3 bits, we kind of fall out of this 192 to 223. So that's 2 to the 21st power, or 2,097,152 networks. The host portion here is only 8 bits, so 2 to the 8th is 256, minus 2, which is 254 devices. So as you can see from this slide, the A offers the most amount of hosts, where B is second, and then C is the smallest. Although C offers more networks than any of the other ones, and B offers like a medium amount of networks, and A doesn't have as many. So it kind of gives you the difference between them. And let's not forget about Class D, that multicast address that we use to move the IP MPEG-2 video around our networks. And of course, this experimental research range that we have here, with one being of importance is at 255. If I use all 255s, I'm doing that broadcast. And that's different than the directed broadcast, because that is out of a network. So we also have private IP. So RFC, Request for Comment 1918, is the RFC, and IP has a whole bunch of RFCs if you haven't seen them. These are the white papers that define IP and how vendors and how MSOs and cable operators will implement IP. Very important. IPv6 alone has over 30 of these. So if you're interested in this, this is rfc-editor.org. You can get more information on different RFCs. But this one is of particular importance for IP, is because these particular IPs are private. They are not routable on the internet. They were designed for us to use services like NET, and we're going to get to that. So we have private IP ranges, and out of those ranges we have a Class A. Now the Class A is a 10.0.0.0 to 10.255.255. That's the entire range. But there's only a single Class A network for private networking. So in our cable infrastructures, you'll see the 10 used a lot, but there's only one network. So that's where subnetting and variable length subnetting are very important to break up those broadcast domains into smaller pieces. It's like having 16 million people on an HFC node. The network is just not going to function with that many devices and that much traffic in one domain. So the same thing here. We can't have 16 million devices all in one domain. We need to break it up, and that's where subnetting will come in. And of course, routers. And the Class B, we have 16 different networks, 172 to 172.31. So there's 16 different possible networks here. So we have a little bit, a lot more than the Class A, but much smaller. They're not as big. They're only 65,000 versus the 16 million. And then on the Class C, we have 255 different ones. We have 0, and you might have seen 100, the 100 network for those cable modems. You might have seen 1 if you had a Netgear or a device that's in your home, whatever your access point may be. But you can see it's 0 through 255. And of course, we cannot forget about the link local, which we like to call the DHCP failure address. But this is also an RFC 1918 address that's designed for the operating system to give you an IP address when DHCP, or Dynamic Host Configuration Protocol, fails. As you can see, the range that's there. And it's a single network. So let's take a look. Let's bring it all together here. So we have a Class A range. We talked about the networks. It was 128. We had to subtract 2 because you can't use all zeros. That's the gateway of last resort, 0.0.0.0. And then over here, the number of hosts per network is going to be 16,777,216 minus 2 because we can't use network ID and broadcast ID. And this is going to follow all the way down this chart. So each one of these hosts will be subtracted 2. And the default subnet mask. So the default subnet mask is where we put ones where the network is. And we talked about the A, the first octet, being the network. So since that's the network, we're going to put all ones underneath it to say to the computer or router or switch or whatever device it is, hey, by the way, this is the network portion. In the B, we said the first 2 octets were network, and in the C, the first 3 octets were network. So this is why these are important, to kind of tell the device, hey, by the way, you need to know which is network and which is host. Over here on the network side, we're not subtracting 2 on the B because there's nothing we have to throw out here. And remember on the A, we had the loopback and the gateway of last resort. And on the C, we're not throwing anything out, meaning we don't have to subtract anything. And feel free, if you have any questions, please type them in the chat window at the bottom of the screen. So the question becomes, what if you need smaller networks? So obviously we can't implement a network of 16 million hosts. It just would not operate. The capacity would not be there. The performance would not be there. So we need some type of tool to break up the network. So that's where we're going to bring in our friend subnetting. Now subnetting is going to allow us to take a network and carve it out like a pizza. So just picture a pizza right in front of you, and you're just going to take your pizza cutter out and cut 8 even pieces. That's what subnetting will do for you. And I'm going to show you VLSM where you can take that same pizza and you don't have to have equal slices, meaning that there might be some folks that at your pizza party that can only eat a small piece, and you might want to carve them out fewer IPs, where there's other components in our network that are larger that may need more IPs, and we don't want to waste. We don't want to have to throw out the pizza. So we'll take a look at that. So we're going to introduce this term called classless interdomain routing, or Cider. Cider notation, you've probably seen it with the /30s and the /29s and 28 addresses. If not, here we go. And the idea with Cider is it allows us to carve out smaller networks. It's a shorthand way of running the subnet. So like a 255 is going to be a /8. So examples. There's our 255.0.0.0, and there's our Cider notation. And all it's saying is a slash, and I'm saying there's 8 bits. That's all I'm saying. And then over here, there's 8 bits here and 8 bits here, which is 16, as you can clearly see in the subnet mask in binary. And over here, it's a /16. And again, we're just going to add this up, 8, 8, and 8. Well, that's a /24. So what we're saying here is you can actually write a Cider instead of writing out the full subnet mask. It's a little bit easier to write that out. So let's first start off with that concept. By the way, if you're interested, we do have SCTE ARIS handbook that has the conversions for all the Ciders and all the default subnet mask. If you're interested, it's a free download for SCTE members. So just wanted to share that with you. And I'm just going to highlight here the bits that we're talking about here. So how do we create a subnet? So how do we carve out a bigger network into smaller networks? We have to answer a few questions. And the first question is, well, how many networks or hosts are you looking for? So you really have to think about this. If I wanted to divide a network into multiple pieces, well, how many networks it is? Is this a network that will cover 5 head ends, or is this a network that will cover 3 different networks within that head end? So you're really going to think about how many networks I have, or how many networks I need, and how many hosts do I need per those networks. So you don't want to take a Class C and carve out 8 networks and then realize that you don't have enough hosts on each one of those networks. So it does take a little bit of planning. But once you figure that out, that's the first question you have to answer, is this one here. The second question is, how many bits do you need? So, you decide, okay, well, how many bits do I need? I decide I need 8 networks. So there's going to be a little bit of conversion. Well, 2 to the what power gives me 8. So that's going to tell you how many bits. So in this case, 2, or if it's 16, 2 to the 4th equals 16, so I need to borrow 4 bits. And I'm going to borrow them from my host. I can't borrow it from the network. And then what is my delta? The delta is the change. And the change is basically how's it going to change from one subnet to the next subnet to the next subnet. And we'll take a look at that. So, and then what happens, once you have your delta, you can write your ranges. What the first IP address is, what the network address is, what the last IP is, what the broadcast is. So let's take a look. And then at the end, all right, what are my hosts? And down the bottom, what is the new subnet mask? So now that you've borrowed these bits, you need to mask the bits. You've got to tell these routers, hey, by the way, these bits are not hosts. They now belong to the network, so we're going to have to mask those. So we'll take a look at that. Here's a subnetting of Class C example. You're given a 192.168.100.0, which that should look familiar. It's used on the cable modems and typically used to kind of look at the diagnostics. And you need to carve it into 8 different networks. Okay, makes sense. Well, how many networks are hosts? Well, we said it was 8. Very easily. But that's going to be coming from some planning on, if I need 8 networks and they're going to use at this head-end site, how many devices are going to use IPs at this site. So you're going to kind of work it out prior to implementation. Nobody wants to do renumbering, and renumbering is where we have to go back and re-IP everything. And that's another reason why IPv6 looks so nice, is because I don't have to keep renumbering my network, and there's ways to do it a lot easier. So let's take a look at how we carve this up. Well, first of all, what I want to do is break it down into the /24 and say, okay, well, here's what's network and here's what's host. Now I clearly see that only the zeros are my host. I know that I need 8 networks. And if I borrow bits, if I borrow 1 bit, well, 2 to the first is 2. Okay, great. But that's not going to get me where I need to be. If I borrow 2 bits, well, 2 to the second is 4. And that's still not enough. If I borrow 3 bits, well, 2 to the third is, ding, ding, 8. So we're there. So we have to borrow 3 bits. So after I do that, I say, okay, well, these are the bits I'm going to borrow, and these are the bits that I've shaded here. They're going to be the host bits. So we're just kind of marking what we're borrowing and what we're leaving for host. So notice there's 2 to the 5th here, or 32 hosts per subnet, minus 2, 30 hosts per subnet. So if you do carve this into 8, and you realize, well, you know what, I need 45 IP addresses, you're just not going to have enough there. So that's why this is important. That's 2 to the 5th. So learning those 2 to the powers and using that chart is very, very helpful. And you'll find that in the, well, we just put the link up there under the resources there in the tool section. All right, let's continue on. So what is our delta? It's going to be the LSB, or the least significant bit that you borrowed. So in this case, I borrowed 3 bits. Now, you're going to refer to this whole entire octet with that original chart, meaning the 1 really sits in the 128 position. The next one is in the 64, and the next one's in the 32 position, or 2 to the 5th. So the delta in this case is the least significant borrowed, which is 2 to the 5th, or 32. Now, once I have the delta, I can write my network ranges. So let's take a look. So I start off with 0, which is the original IP address, and I keep adding 32. So I keep adding 32, and I'm just going to move that 0 out of the way. I keep adding 32, and I should have 8 what I call front-end networks, because I didn't write the back end. So these are the 8 front ends. If I add 32 and get to 256, we talked about that. You can't go over 255. So then you just say, okay, let me erase that one. Now the back end is going to be the broadcast, which is the last address. Notice this is 31, and the next one here is 32. So there's always one less here. And the next one will be 63, and so forth and so on. So you can see all the addresses there. The last one is 255. So you can see that the first range is the original network ID. The last one has the original broadcast, and that used to be a problem at one time. But today, you might have to put in the IP subnet 0 command in your routing device to handle that. We used to have to subtract these out of the subnets as usable, but that's no longer the case. And here is your ranges. So now that I have my ranges, I have my broadcast and network IDs. What are my hosts? Whoop, let's go back here. Here they are. So I have my hosts 1 through 30. Notice that I can't use 0. That's the network ID, and I can't use 31. It's the directed broadcast ID. So here's the 30, and there's the 1. And we'll come over here. We borrowed 3 bits. In the beginning, we had 24 bits in the subnet mask. We borrowed 3 more, so that's going to give me 27. So here's my 27. So I got 27 bits in the subnet mask, and here they are in binary. And I come down here, and here's what they look like in decimal. And how did I figure that out? Well, this is 128 plus 64 plus 32. If I added that all up, if I add all that up, I get to 224. Subnetting in Class B, very similar, except this, you just kind of try to pay attention to what octet that you're in. So here I have 4 networks on a 172.30. Okay, how many hosts, how many networks? Why, we said 4. We come over here, what does it look like? What's hosts? Well, here's what's host, and here's what's networks. We said 4 networks, and 2 to the what gives me that? Well, that's 2 to the 4th, so I'm going to borrow 2 bits. Makes sense. There's my 2 bits that I borrow, and the rest is host portion. So if you want to know how many hosts per subnet, take all those up and add them up and take them, so that's 8, and it looks like 6, so 8 and 6 is 14, so 2 to the 14th power, which is what, 16,384 minus 2 per subnet. Come over here, we borrow 2 bits, there they are. What is the delta? Well, it's the least significant bit, it's the second one. So the 2 to the 7th would give me the first one, and 2 to the 6th would give me the next one, which is 64. Then I write my ranges. So I start at 0, and make sure you're working in the 3rd octet. That's the biggest mistake here. Some people think, oh, well, it must be that octet. No, you've done the work in the 3rd octet. Stay in the 3rd octet. And then we'll come out with our broadcast. And the broadcast, notice that if 63.255, I added 1 more value, it's going to dump me into 64.0. It's going to dump me in the next range. So that's how we know it's the last one. And of course, the original directed broadcast should be what you end with. The original network ID is what you start with. And then the last piece is, well, what is the new subnet mask? Well, I take my 16 bits that I had to begin with. Oh, we're still doing host ranges. So our host ranges is 1 plus the network ID. Over here, the directed broadcast is 1 minus the directed broadcast ID. Those are all valid hosts. We talked about that subtracting 2 early on. The new subnet is 16 plus the 2, which is going to be a /18. And then what does that look like in binary? Well, there you go. And what does that look like in decimal? That's 192, because a 128 and a 64 is 192. So that's subnetting. Now, the problem with subnetting is you're giving everybody an equal pie, or you're giving everybody an equal number of IP addresses. Well, that might not be the best way to do it. Especially, I might only need 6 IPs. Well, here you go. Here's 270. Well, I don't need that many. I only need 6. Well, don't worry about it. Just waste the rest of them. Well, maybe if you're running IPv6, you can waste. But in IP version 4, we're having a problem with IPs now running out. So we just can't waste IPs. So it's very important that we use them the best way we can. So they came out with variable length subnet masks, where each subnet can be a different size. So let's take a look. So again, here's what it stands for, variable length subnet mask. And coming down here, it allows you to calculate these different networks. So if I have 4 different networks that need to be IP'd, I could start out by putting them in size order. This is one method I like because it makes it easy. So if I have, we'll see that coming up. And then the other thing, that once I figure out what the size order is, or who needs the most IPs down to who needs the least amount of IPs, then I have to ask myself, well, what is the block size? So a block size means if I need 500 IPs, the closest block size to that would be 512. Because binary only deals with powers of 2, and we might need 500 networks that we're thinking decimal, binary is thinking base 2. So the closest you can get to 500 IPs is a block of 512. The closest you can get to 25 IPs is a block of 32. There's a bit of waste here, but not too much. But those are the first thing to understand is the block size. Obviously, you can't have a block size of 2 because you got to subtract the network ID and you got to subtract the broadcast ID. So there goes that. You'll have 0 IPs. And once we have the block size, it will determine how we're going to VLSM. Now, the difference between VLSM, another operational difference, is that we're going to work from right back to left. And the previous examples, we've been working left to right. And then we're going to calculate the subnet mask for the network, so we'll show you that. That's coming up here. So let's take a look. So we're going to have a network, and let me just go one more slide here. Here's our network that we have. We have Area 1, 500 users, Area 2, 60 users, Area 3, 200 users, and then between these routers here, we have a /30 or a point-to-point connection. So we come back over here. we're going to say, all right, we're given this class B 172.16/16, and we need to carve out a 500 network, a 600, a 200. And we said we want to put them in order. So 500 would be carved out first, then 200, then 60, and that point-to-point would be a block size of 4 because we have to subtract 2. So let's take a look. Let's come over here. So list the networks in size order. That's what we're going to do first. So here's our size order. It looks like area 1 is going to be the largest, area 3, and then area 2. Once I determine the size order, if I want to throw that point-to-point, that could be under here as area 0, if we want to call it, and that's 4 users because we're going to have to subtract 2. So if we had a network that needed 8 users or 8 IPs, and then we say, okay, well, that's fine. I'll do a block size of 8. Well, when you subtract the network ID and the broadcast ID, now you're down to 6 IPs. So that's a simple trick that can throw your networks off. So make sure you always plan strategically when determining how many IP addresses you need. So the block size for these is very simple. What's the closest block that will get there? Well, 512, 256, and 64. That's the closest block that we can get to get that. Okay, makes sense. And I got my block sizes. Let's continue on. So in area 1, we said it was 512 is the closest blocks because 2 to the 8th is going to give you 256. 2 to the 9th is 512, and that's the closest we can get to 500. If we do anything less than that, it won't be 500. If we do anything more than that, we're going to waste IPs. So that means we have 23 bits for the network ID, and then we're going to have 9 bits for host, and we're going to subnet everything else. So it's working a little bit different. So in this case, my least significant bit is that 2 right there in the 3rd octet. And always pay attention what octet you're working with. So in this example, the range is 172.16.00 through 172.16.1.2. Why? It's because the next one's going to start at 2. So you start at 0, then you count by 2s because that's the delta, and then 2, and you stop. Because with VLSM, all the networks are different sizes, so you're not going to keep subnetting one after the other to keep making these equal pizza pie slices. You're now going to create a different size network. So you're only going to carve out this first one and stop. So our next network begins at 172.2. So let's take a look at that one. So area 3 is a 256 block, and notice for 256 IPs, 2 to the 8th will give me that 256 IPs. We only needed 200, so we have plenty of growth. Over here we're going to start at the 2 because that's where we left off. And in this one case, the delta is 1. That's the least significant bit borrowed. So we just count by 1. 172.16.2. And the next network would start at 172.16.3 because 2 plus 1 is 3. Continuing it on, area 2. Block size is 64 because we need 60. Minus 2, 62 is plenty. And to get 64, it looks like I need 6 bits, 2 to the 6th. So my least significant bit here would be this bit right here. So I start at 172.16.3. My delta in this case is 64. And I will go from 3 to 63. And I'll leave off at 64. And that's where I can throw a block size of 4 for that point-to-point. So if I wanted to, I could pick that up at 172.16.3, 64. And that would go to the next starting one would be 172.16.3, 68. And then you would have an IP address 65 and 66 for your point-to-point, if we threw that in there. So we break it down for you, what it looks like. So here we have our network ID, our broadcast ID here for the first network ID, broadcast ID, network ID, broadcast ID, and you can see the host ranges for each one of these.
Steve, before you move on, we have a question from the audience.
Oh, yes.
Okay, you may have covered this already, but if so, if you could just summarize. When you're calculating the block size for VLSM, why is it that we subtract 2 from the total block size? Okay.
Yeah, going back, thank you, Susan. Going back to our earlier discussion in one of the earlier slides, and the jump back there would be, might be a little bit funny with all the animation I have. But the reason we're subtracting 2 on any of the networks on the host portion is because we have the network ID. The network ID is always zeros in the host portion. So we cannot use that because that is an identifier to a router or host. Hey, this is the network address and this is what network I'm on. If we try to assign that out, some operating systems bark at you and say, hey, you can't do that. And then the other address that we have to subtract out is that directed broadcast. This is the way devices communicate on a broadcast domain. And if we assign that out, there's no way for these devices to communicate, especially when you get into just some of the TCP/IP protocols that need to communicate within that broadcast domain. So we have to subtract 2. and for VLSM and both for subnetting.
Thank you very much.
Oh, thank you. So let's take a look. Now we've covered VLSM. Just before I jump into IPv6, I just want to mention one of the other things that you might want to jump on is once you start practicing some of the VLSM and start practicing some of the subnetting, is then to start getting into wildcard masking. Wildcard masking is another way to manipulate the bits, and that's going to lead you into route summarization. Route summarization allows you to take a series of networks and then combine them into a single network address. Sometimes not the best thing for our routing tables in the cable industry, because we want to do some troubleshooting, and if we mask or if we hide all the networks under one address, it kind of makes it a little bit cumbersome to troubleshoot. But those are just other areas that deal with IP version 4 addressing that you'll run into in our IP infrastructures that you might want to take notice to. So IPv6, well, we threw this in here because IP 101, you cannot do IP 101 with a little bit of IPv6. And the reason for that is that the IP version 4 is running out. So here you've probably seen these. If you have a smartphone, you can download this little app that runs on your smartphone, whether it's a Droid or an iPhone. They have this thing called Bye-Bye4. And it's like a little time clock that says, okay, well, you're going to run out on this certain date and this certain time. Well, they don't really have a time there, just the date and the days. And how many whole blocks do we have left? And this one's showing 12. Now, since this slide deck has been created, we are actually lower than that. There's actually 11 blocks now instead of the 12 blocks. And we are down running out around March 12th. So this is the Internet Assigned Numbers Authority. This is going to run out on March 12th of 2011. So this is right around the corner. And what's the big deal about IANA running out? Well, considering that we're in North America, the American Registry of Internet Numbers supplies IPs to all of the North American cable operators and MSOs, and if they go there to Aaron and say, hey, we need some more IPs, they go to Aaron, Aaron goes back to IANA and says, yeah, I need some too. Sorry, we're out. So I guess there's a good thing here. IANA runs out, but that doesn't mean Aaron's going to run out right away. And Aaron is where all the operators get their addresses. That's going to be December 8th. Now, this is just a clock. Some people don't like this clock because there could be all of a sudden a run on IPs as we get closer and closer, meaning that this clock might say March, but we could run out in January. So these are just estimating. So just to kind of be aware of that, say, well, there's no more IPs and it's only January, but Steve said we can wait till March. And again, this is just to kind of give you an indicator. And I'll give you this, if you would like to follow along, I'll give you this link here. Let me see if I can pop this out to you. Yeah, both of them are going to be 2011. So this is IPv4 Podaroo. Oh, I'm not typing. That helps. Let's see. And when I get done here, I'll type this. I'll type this link in. But I'll give it to you right now. It's IPv4.podaroo, POTAROO.net, and it's a little clock here that I have, and they have a website as well that you can view. Current projections again is mid 2011. I just told you it was March. It's running a little bit faster. You might have seen Barack Obama talk about his recent directive that says all U.S. government agencies must upgrade their infrastructure to support IPv6. So, there's a government mandate here for its infrastructure, as well as there's already cable operators, some as early as 2005, that have been implementing IPv6 in their core and ag networks. And the reason why we haven't, how people ask, well, why now, Steve? Why all of a sudden now? It's because we had Cider. We could actually carve out and use the IPs a lot better with VLSM, so we didn't waste as much. We could subnet, and now that Class A can be used for multiple networks. We came up with private addressing. So private addressing sits behind a NAT, and all the NAT does is take that private address that everybody in the country is using and converts it to a public address. So you can have a single public address shared with 256 minus 2 private addresses. So these are things that extended the life of IP version 4. So that's why now, because we're running out of the the public addresses to put on the other side of those NAT, or network address translation routers. So what's going to really change? Well, it's 128-bit. That's a big deal. So 2 to the 128th power is a huge number, and we're going to take a look at that. But that's the first thing. It's not 32-bit. It's 4 times the bit structure of IP version 4. It's hex. So now you got binary, learn some binary, well, you better start learning some hex, especially binary and hex to understand subnetting in IP version 6, which is a lot easier than 4, but you still have to have the foundation of binary and hexadecimal. We got rid of the A, B, and C. It's a hierarchical structure. It works more on scopes, and I'll share them with you coming up. It's no broadcasting, which I mentioned, so you're going to see something, any cast, more multicast being used. We did a fixed header on IPv6, which is nice. It's going to be more streamlined. It's going to route a lot better. IPsec is built in. Yes, security is an issue, so IPsec is integrated into the IPv6 stack at the network layer. The checksum, we got rid of that because why should IP do checksums? So we've moved that out. Of course, TCP has some checksums in there. We also have the Ethernet layer doing some checking, CRC stuff for us. And then UDP, there's an optional header checksum that can be added to the user datagram protocol. So that kind of, instead of having IP deal with it. Mobility support. So mobility, we've had some issues with triangle routing, not enough IPs where I can keep my IP. So now I'm using my cell phone over in Europe, but now I'm using a different IP. How do I route packets back to that mobile phone? Because the IP keeps changing, that's always been an issue, so those are resolved with IPv6. So here's what the address structure looks like. Very easy graph. You can see it's huge. And here's the value. This is 340 undecillion, or 340 trillion, trillion, trillion. So you can see it's a very large number. If you take that number divided by 7 billion, it's just a humongous number for every person on Earth, how many different IPs there are. So it's a huge amount of IP addresses. So that's a big thing. We're never going to say you never run out, because I'm sure in 1970 and early 70s we said, we'll never run out of IP version 4. 30 years from now, I'll be like, I can't believe we ran out of IPv6. So we're not going to say that. We're going to say there's a lot of IPs that are out there, and we should get us for the next 30 years. Another note I'd like to make, even though you see IPv6 coming out, don't think that IP version 4 is going anywhere anytime soon. So it's one of those things where we have analog, and we're not going to get rid of analog. That's not going to happen. We're always going to have some analog sitting out there along with digital. We're always going to have IPv4 sitting out there along with IPv6. So it's not something that is going to go away. This is the address structure, just to show you. These what I like to call hextets. They're not octets or hextets because they are 16 bits apiece. So there's 16 bits here, 16 bits here. There's 8 sections. So 8 times 16 is going to give you that 128-bit. 39 characters if you include the colons. Now over here, the network ID, you can see the network ID is about 31 to 32. This is the prefix that you'll get from ARIN, the American Registry of Internet Numbers. Over here, you are able to carve out, or the operator is able to carve out, /48. That means this will be 48 bits. These are Cider Notation that we learned earlier. 48 bits in the network ID. Well, then you're giving the customer, or you're giving the device 64 bits plus another 16. You're giving them a crazy amount of IPs. So you'll see more of like a Resi install. So if you get an IPv6 address and you're going to run, like you're an IPv6 customer for a cable operator, it's probably typical as a Resi customer getting a /64. But you're still getting 64 bits just for the network ID. So if you take 2 to 64 and plug that into your calculator, you'll see that's a huge number of IPs just for your home network. Like, well, how am I going to use all them? So that's the basic structure. The component in red, that is really where a cable operator comes in with their address plan to really carve that up the way it makes sense. If we carve the interface ID up, you can't use some of the automatic addressing features. Let's continue on here. So we have zero compression. I just wanted to point this out to you because this is something that's important as we go through. Let me just back up a little bit. So what we have at the top is a full address, and it's all hex digits here. So that's where you see the C and the B and everything. So we have all these hex digits up here. What we can do is some zero compression. You have 2 rules that apply. So the first rule is you can drop leading zeros up to 3. So these 2 can be dropped, and you can compress using double colon. From left to right is typical. We don't really double colon to the right and then back. But you can only use 1 double colon. So just to show you how this is built out step by step, if I bring this down and I just do 0, I can leave off 3 leading zeros. Here we go. And then down here I can lead off these 2 leading zeros. There's C3. And so forth. There is that 2A that was dropped off, and we have the 2 zeros that were dropped off here, and that's pretty much it. Taking it a step further, which is now going to use that double colon rule. That's what the computer is going to do, is going to drop those. That 0 is going to turn into a double colon. And once that's used, that's it. Because the interpreter is not going to understand where to put all the zeros back if you use 2 sets of double colons. It doesn't make sense. So it's only going to be one of those. And you notice where all the zeros were dropped off, I'm pointing to it, and remember to use the colons once. Now the other important fact of IPv6 is scopes. So what I'm showing here is link local. And link local you're familiar with because that's the 169.254, and link local is very, very important. Without a link local address, which is a link local will automatically configure itself. So this is called Slack, stateless address auto configuration. You can automatically configure link local. So you might have seen us doing an IP config command like, what is FE80? And the rest of it's made up from your MAC address, or if you're Windows, you get a little bit secure. I guess you want to be a little bit more secure, so there's like a pseudo random generator to make up the rest of the address. But you may see that doing an IP config command on your computer. The ULAs, or unique local address, they're going to be the replacement for the private addresses that are used today. So they start with FC00. And then the global unicast, which most of the operators are going to have, are going to be a 2000 address. So when you get done this call, check back with your operator and say, what is our global unicast prefix? And there's ways to look it up on the internet. So these are a scope, and the scope means that global everywhere, ULA will be within your infrastructure, within your intranet, or within your company, and link local will be within a broadcast domain. Even though broadcasts don't exist, it will kind of operate in that area. Other addresses, : that's unspecified, and then we have the gateway of last resort address that you've seen there early on. That's also could be used as an unspecified address, typically used in a packet for DHCP. Come over here to loopback, : 1. You can very easily go down to your command prompt, type in ping space : 1, press enter. You'll ping the loopback or the TCP/IP version 6 stack on your NIC card. Multicast, we know it's FF. Well, we don't know that. We know it's 224 in IP version 4. It starts with FF in IPv6. So these are just some of the important addresses, scopes, and types that you'll kind of run into as IPv6 comes to your neighborhood. The header, here's what the header looks like, cleaner. It's a 40-byte header, so it's fixed. And you can kind of see there's a version. Traffic class is going to be your quality of service. Flow labels still being implemented, but it's more the flow of how that packet's going to transverse through your network. You have a payload length, but not the whole entire packet length. Next header, this is how you tie in all the optional fields into the IPv6 header, so this will scale. It's not that let's keep adding things to IPv4 header and make it break, like diffserv code point was added in, and not really it's diffserv code point making it break, but it's something that did not exist within IP version 4 header that we had to add. And of course hop limit, and then your source and destination address. And then what about IPv6 address support? Well, you say, well, I don't know who's supporting it. Well, obviously, if you're a Linux fan, Linux supports it. You got Macintosh out there. Here we can see some AIX, some Unix operating systems. Cisco, obviously, and Juniper is out there. So the routers, I know that Eris is getting IPv6 ready and supports IPv6. So there's a lot of vendors out there that support IPv6. I just don't have the time to mention every one of them. So I did this small little, or Paul did this rather, this small little chart here that kind of describes, yes, Linux, here's Mac, here's Solaris, here's Windows XP, Windows Vista, Windows 7. They support IPv6. And all you have to do is go into your network properties, and you can actually just hit a checkbox and turn it on. And you can get an FE80. So you can literally go home tonight and all your devices turn on IPv6, and you could be pinging FE80s across the house or across your network and have an infrastructure set up, a link local, and you can be running IPv6 within your network. And then some of the routers now, the access points are coming with patches that will support IPv6, so be looking for that. So in summary, know your binary. So this is 101. Paul's a learning development professional from Comcast, and I know that one of the things that he teaches Cisco classes over there, and one of the things that are challenges is that binary, to really understand the addressing. Yes, you can use charts. That's fine. A lot of people have binary charts that convert the number for them, but to really deep dive into IP, know your binary. Whether it's 4 or 6, you're going to need the binary. So know your binary. Very important. And I'm going to parlay off the binary and say also know your hex. Very, very important. Subnetting allows you to segment large networks. So the reason we use it is that we can't. It's the same principle that we do node splits. We can't have nodes with 2,000 customers on the node. The customer experience just would not be there. So the same thing here. We're not going to have a good customer experience if all our IP packets are taken forever to traverse the network because there's just too many devices in that broadcast domain. So subnetting is going to help us segment the network, and using routers, we'll be able to break up those networks into smaller networks, more efficient networks, and route IP much better through our infrastructure. And then VLSM is going to maximize the subnetting. So subnetting came out first, and VLSM says, well, you know what, I can maximize this. And I can say I'm not going to waste any IPs because I'm going to give everybody a slice that they need as close as possible to that block size. And then IPv6 is coming fast, whether you like it or not.
Thank you very much, Steve. I would like to invite our participants to submit questions at this time by typing a question into the chat window at the bottom of your screen and then clicking send. Our first question is, Steve, you mentioned that Class D is used for multicasting. Can you define multicasting and talk about that for a minute?
Okay, that sounds great. Thank you, Susan. So multicasting is what we refer to as a group. So multi meaning many, and multicasting is casting, is sending messages to a group of devices on the network. So this is critical with our IP video transport. We use the multicasting to direct IP video packets to devices on our core network, so we can control. And so I guess the big picture is we don't have to have multiple copies of the same thing. We can actually say, okay, here's one copy, and we multicast it out, and everybody gets that one copy, instead of having 200 copies of the same thing. So multicast is going to have efficiencies within our network. It's going to allow us to communicate to a group, and they're going to have a whole pile of new features that are in IPv6. So multicast is going to be there as well.
Okay, great, thanks. In IPv6, what's the difference between unique local and the link local addresses?
Okay, so the key there is the scope. So if I won't switch the slides there, but the scope is the key difference. So a link local that we used to say in IP version 4, we say, well, there's something wrong here, and it's usually a DHCP failure, and nobody likes to have that 169. So in IPv6, the FE80 is a link local, which is very important for communication. So once you get an FE80 in IPv6, your laptop, say for instance, it's going to actually do some router solicitation, and it's going to say to Mr. Router, what is my DNS? What is my default gateway? Do you have any information for me so I can configure myself? And I'm going to take my link local, and it's going to give me a global address. And that's the importance of link local, but it's only within a broadcast domain. It does not pass over a router, or in this case, a home router, CPE device, or a CNTS. A ULA, unique local address, is a scope that's very similar to private addressing. So within private addressing, just to give you this, which I did not mention, a ULA can be globally unique. There's actually 41 bits, or 2 to the 41st power, well, minus a bit. So it's like 2 to the 40th power, different types, or the 2 to the 40th power private networks exist within IPv6. So it's private networking that an infrastructure could use, and it would not be routed on the internet. That's a difference. So to sum up, ULAs are not used on the internet and they're used for private networking. A link local is critical for IPv6 communication and used within a broadcast domain. It would not pass a router.
Okay, excellent. Thanks, Steve. While we're finishing up here, Steve, could you type in the address for that countdown app that you referred to earlier?
Yes, I'll do that. Yes.
Okay, thank you very much. And just want to let everyone know we have recorded today's presentation. You'll receive an email within a couple of days when the recording is available. It's available for SCTE members. And I'd like to thank today's author, Paul Rodriguez of Comcast, and our speaker, Steve Harris of SCTE. Next month, SCTE Live Learning returns on Wednesday, December 15th, with Trends in Cable Telecommunications, What's Next? Our speaker then will be John Patifio, a systems engineer from Cisco. And at the conclusion of today's session, you'll have an opportunity to register for the December presentation. SCTE appreciates the support of Cisco Systems, sponsor of SCTE Live Learning. There are additional slides with examples of subnetting at the conclusion of today's presentation. So please check the link to the slides that was emailed to you earlier today, and you'll see those slides, those additional slides at the end of the slide deck. Ladies and gentlemen, that concludes today's SCTE Live Learning webinar. Thank you for joining us. We look forward to having you back again next month.